Today is Thursday, 27th of May, and this is day section 2 of AGMA. I saw for a moment Yaryna, and it is my pleasure to invite Yaryna Stelmakh to open this session with her talk, which is Homeomorphisms of the Space of Non-Zero Integers with the Kirch and Golomb topologies. Good luck, please.
My name is Yaryna Stelmakh, and I'm from Lviv, and today I'm going to speak about Golomb and Kirch topologies on the set of non-zero integers. First about Furstenberg topology on integers. The Furstenberg topology on the set of integers is generated by the base consisting of arithmetic progressions a plus b z, where a belongs to z and b is a natural number. Furstenberg topology was introduced in 1955 by Hillel Furstenberg, which he was a Nobel Prize laureate when he was an undergraduate student in Yeshiva University. Furstenberg used this topology in his famous topological proof of infinitude of the set of primes. The Furstenberg topology is regular, and being second countable, it is also metrizable. By Sierpinski theorem, the space that endowed with the Furstenberg topology is homomorphic to the space of rationals Q. Consequently, it is topologically homogeneous. Now about homogeneity and rigidity. A topological space X is called topologically homogeneous if for any x, y from X, there exists a homomorphism from X to X, such as X equals Y. And what is topologically rigid space? If H from X equals X for any X in X and any homomorphism H from X from space X to X. And a few one example, a space that endowed space that endowed with Furstenberg topology is homomorphic to Q, and hence it is topologically homogeneous. Now about Golomb and Kirch topologies on integers. Number, for some examples, number is called square free if it is not divisible by the square of any number. And two numbers called coprime if they have no common prime divisors. For example, numbers 2 and 3 are coprime because they have no common divisors. Numbers 0 and 1 are also coprime, and numbers 0 and 2 are not coprime. What is the Golomb space or Kirch space or space with Golomb-Kirch topologies? The Golomb and respect Kirch topology on set of integers is generated by the base consisting of arithmetical progressions a plus bz, where a is from z and b belongs to natural numbers. And when the space is Kirch, b is square free number. When the space is simply Golomb, the space is Golomb, it is the b is coprime with a. And this example, the unique neighborhood of 0 is 0 plus 1z, so it is z, and consequently the space of integers with a Golomb or Kirch topology satisfies the separation axioms T0, but not T1, because you cannot separate 0. And now about the Golomb and Kirch topologies on the set of integers without 0. The subspace that without 0, there integers, is Hausdorff in the Golomb and Kirch topologies. The same is true for the subspace N of non-zero integers, space natural numbers. It is Hausdorff in the Golomb and also in the Kirch topology. Surprisingly, the subspaces N and Z of non-zero space of natural numbers and non-zero integers with Golomb and Kirch are countable, second countable, Hausdorff, and connected. This follows from the fact that for any arithmetic progressions A plus Bn with coprime A, B natural numbers, the closure of A plus B n in the Golomb or Kirch topology contains the arithmetical progressions Pn for any prime divisor P of B. Consequently, for any non-empty open sets U1 and U1 for any natural number n, this open sets belongs to n or z with the Golomb or Kirch topologies and their intersection. So you can see closure U1 intersection of their closures is not empty. And the last property that this intersection is not empty is called superconnected. And these spaces are also non-matricial. And now about the rigidity of the Golomb and Kirch topologies on a set of natural numbers. Let us recall that the space of integers endowed with Furstenberg topology is homomorphic to Q, to rationals, and hence is topologically homogeneous. On the other hand, the Golomb topology has the opposite property. The space N with Golomb topology is topologically rigid. The analogous result holds for the Kirch topology. And there's also the theorem that space N with the analogical theorem with the space N with Kirch topology is also topologically rigid. And these were homomorphies on the set of natural numbers, and now they're also homomorphies on a set of integers, non-zero integers. So this space of non-zero integers endowed with Golomb or Kirch topology does admit a non-trivial self-homomorphism, the involution J from Z from non-zero to non-zero integers. And so we have the theorem that the space of non-zero integers endowed with Golomb topology admits only two self-homomorphisms: the identity, as in previous case, and the involution J. Analogous result holds for the Kirch topologies of non-zero integers. So also the space of nonzero integers endowed with the Kirch topology admits only also two self-homomorphism, the identity and the inverse. This proof is quite long, consists of your lemmas, and it exploits order properties of some set of filters determined by the superconnectedness of the Kirch topology. So that's all. Thank you for your attention. Your your phone is off.
Yeah, thank you for the talk.